So hello Year 12, and I hope things are going well for you wherever you are and that you're looking forward to the Easter holidays. Who knows whether for any of you that will look any different to your current weeks. Probably less work and more boredom. I will put the mark scheme directly online for anybody who would rather just work through the mark scheme by themselves. But for anybody who wants me to go through the mark scheme with them, either because you like me to point out errors or because you love the sound of my voice, then I shall do this for you. Completely voluntary, just going through those questions I set you at the start of the week. So, if we look here, first question, 4.17 grams of phosphorus 5-chloride reacted with ethane dioic acid, forming phosphorus oxychloride. You got the equation there. The phosphorus oxychloride hydrolyzed by water as shown in the following equations. Calculate the total volume in decimeters cubed of hydrogen chloride gas produced by both reactions. Well, the first thing is we've got 4.17 grams of phosphorus 5-chloride. It's the only thing we can immediately work out the number of moles of, so we should do that. Once we've worked out the number of moles of that, then we want to work out how much HCl is produced. Well, 1 mole of that will produce 2 moles of hydrogen chloride, but then this thing goes on to produce another 3 moles of HCl. So overall you get 5 HCl molecules, moles produced from 1 mole of PCl5. So the mark scheme looks like this. You calculate the number of moles of PCl5 for 1 mark. You recognise that there's 5 moles of HCl for 1 mole of PCl5, and that's your second mark. Finally, you need to use this information that 1 mole occupies 24 decimeters cubed at RTP, times it by 24 decimeters cubed, and you get that the final volume 2.4 decimeters cubed. Allow arrow carried forward for steps in calculation. Ignore significant figures in the final answer except 1. That's a common thing there. They haven't told you how many sig figs to give it to. Just don't give it to 1. But also don't round. If you make a mistake earlier on and you round, then actually you can lose marks later on for incorrect values. We're given a titration here. We're told to complete table 1 and let's calculate the mean titer. This is clearly 23.15. This here, the difference between these two is 22.25. I'm doing this off the top of my head. The one to be careful of is here, which is 22.30. Do make sure you record everything to the right degree of precision, okay? And that is true of the two on the right here as well. So the mark scheme, calculate all the titers correctly, giving the zeros notice. That's for 1 mark, and then you realise concordant titers 2, 3 and 5. You might be wondering whether or not it's 0.2 or 0.1 centimetres cubed. Hopefully it will tell you in the question. If it doesn't, just use a bit of intelligence. Here it's quite clear that the ones that are way out are 23.15 and 22.70. All the others are in fact within 0.1 of each other, so it wouldn't have mattered which value you took. And I think the questions will be structured like that. Trichloroethanoic acid has got this formula. Calculate the concentration of trichloroethanoic acid in grams per decimeter cubed. Give your answer to 1 decimal place. So this is a fairly standard titration question here, only we've got to do a final conversion at the end into grams per decimeter cubed, and that's why it's in bold. Okay, so calculating the number of moles of sodium hydroxide, which is concentration times volume over 1,000. That's the number of moles of sodium hydroxide. And the first mark actually is for realising that the number of moles of trichloroethanoic acid is that because of the 1:1 ratio up here. Once we've worked that out, as is standard in a titration question, we then work out the concentration of the unknown. Concentration is moles over volume. Again, not forgetting the factor of 1,000 in then to get 0.146 moles per decimeter cubed. Finally, we've got to convert that into grams per decimeter cubed here. So we need the formula mass, 163.5 grams per mole, times that by the concentration, and that will give us the number of grams per decimeter cubed. So all we've done is we've converted the number of moles in 1 decimeter cubed to the number of grams in 1 decimeter cubed. So that's your straightforward moles is mass over mR equation there being used in the last part, in case you hadn't quite gotten that. Okay, next, show by calculation that the percentage purity of trichloroethanoic acid is less than that claimed by the manufacturer. Okay, so the manufacturer gives us the number of grams in 250 centimeters cubed. We've calculated the number of grams in a litre, so we've calculated was it 23.9? Let's look back. Yeah, 23.9 grams per decimeter cubed. So if there's 23.9 grams in a decimeter cubed, then we can work out the number of grams that would be in 250 centimeters cubed, which is that. The purity is the amount we've calculated over the total amount that should have gone in, which we're told earlier in the question, times by 100%, which is 96.4%. So we can work out that that is a lot less than 99.9%. The other thing you could have done was you could have said, oh, well, we know we got 6.2 grams in 250 centimetre cubed. That would be the equivalent of 24.8 grams in a litre. And again, we could compare what we worked out in the previous part, 23.9 grams per litre, with the amount we've just calculated there should be. Gives us the same answer again, less than 99.9%. So 1 mark for calculating the number of grams in 250 centimetre cubed, 1 mark for percentage purity, or doing it the other way round. Either way, 2 marks for that. We've got some uncertainties here, and we've got to complete the table. Now, when we're measuring things, remember that you need at least 2 mass readings. So you either zero the balance, that has an error associated with it, and then you weigh it, or you weigh by difference. In either case, there are 2 mass readings there, okay? So if that's the uncertainty per reading, the total uncertainty must be plus or minus 0.1 in terms of what the total error is in the mass reading, and therefore you can put that relative to the mass and work out what the percentage error is. The pipette volume, we don't double this, okay? So things like volumetric flasks and pipettes, which we just fill up to the line, there's only 1 reading we do, and that is how close you are to that line on the pipette or the burette, and therefore we don't need to double that. So looking at the answers, each mass reading, well, there's 2 of those, so that's 0.1 over 6.2 grams times by 100%, 1.61%. And the pipette volume, we don't double. The total error in the pipette is 0.04 centimeters cubed. The amount taken was 25 centimeters cubed, so that's 0.160. Okay, do make sure you're recording it to the appropriate precision, which looks like it is 3 significant figures. This question really caught people out. I'm not sure whether you've seen this one before, you've probably forgotten it anyway. The total percentage error for the experiment can be estimated by adding together the 4 percentage errors. Explain whether the manufacturer's claim that the acid is 99.99% pure is correct. Okay, so we've worked out that actually the acid is 96.4% pure. And that's from a couple of goes ago. So 96.4% pure. That's what we worked out it was. And on the previous slide, we can see here that if the percentage error up here is 1.61% and this is 0.160%, and we can sum all of those together, which I'm just going to do now. 1.61 plus 0.2 plus 0.16 plus 0.449, 2.41%, okay? So that sums up to a total error of 2.419%. So we know here that that is 96.4% pure plus or minus 2.42%. So that means that the minimum value that can be, assuming that there's no mistakes made, is 95.0%, and the maximum value that can be is 98.8%. Sorry, that should be 94.0, shouldn't it? 94.0, because we're taking off 2.4%. So the range that the actual stuff could be is between those two, and clearly that is not compatible with 99.9%. So even taking into account the error in the experiment, which is 2.4%, that cannot be right. So the total error, 2.42%, claim is not correct because the amount we calculated it was plus 2.42% is still lower than 99.9%. Told you these had come up. 3 issues with the technician's method, and for each identify an improvement. You do need to know these core practicals well. This was CPAC 3, doing a titration. So what are the errors? So, didn't accurately weigh out the mass of the solid. It would be much better to weigh the mass of acid by difference, or rinse out the weighing bottle. Or you could have said use a balance reading to more than 2 decimal places using a more precise balance. Notice here, reject a more accurate balance. It is demanding that you know the difference between something that is precise, that is recorded to a lot of figures, and something that is accurate, that means close to the true value. Hopefully your balance would be accurate even if it's recording to 2 grams, 3 grams, 4 grams. No more precision than that. Okay, some acid will be left in the beaker. Some acid will not be transferred into the volumetric flask. Sorry, I've just realised this is actually CPAC 2, isn't it? This is making up a standard solution that it's asking you about here. This was the making up the solution at the start of it, okay? So these are problems with CPAC 2, not CPAC 3. My apologies. Some acid left in the beaker, some acid not transferred to the volumetric flask, and it would be a good idea to rinse out the beaker. Add the washings to the volumetric flask. The solution was not mixed. We need to invert the volumetric flask. Okay, so these are all CPAC 2. And if you go back and you look at my video from last week, I think it was part 2, you will see we discussed these. For CPAC 3 down here, it's the fact that the burette should be rinsed with the acid solution before use. And again, in that video I discussed why the burette should be rinsed with the solution but the conical flask should not. The pipette should also be rinsed with sodium hydroxide, and that was acceptable there. Different experiment here. This is CPAC 1. This is working out the molar volume of a gas. Student used a piece of magnesium ribbon, about 5 centimeters in length. Dilute hydrochloric acid in excess. Repeat the experiment. Calculate the number of moles of magnesium used by the student in each experiment. Moles is mass over MR. No surprises there. Ignore significant figures except one. You hopefully got an answer of something in the region of 0.001667, or if you're using the more accurate number, the value above. Use your answer from part A1 to deduce the number of moles of hydrogen gas produced. It is clearly just a 1-to-1 ratio, so it is just the same number. Calculate, using the ideal gas equation, the volume of hydrogen gas in centimetres cubed. Okay, it's in bold, it's important. We need to give the volume in centimetres cubed that should be produced in each of these experiments. We're given the pressure. We know the number of moles of hydrogen. That's from above, so that is N. We're given R. So we know P, we know N, we know R. We presumably are working at standard temperature, but we've got to make sure that that is in Kelvin, and then we can work out what the volume is. So temperature changed to Kelvin, 1 mark, 297 Kelvin. Rearrangement of the equation and substituting in the numbers. This is something that students always miss. They always don't do this mark, which is fine if you get the right answer, but if you don't, you've lost a mark unnecessarily. Rearrange the equation. Write down the rearranged equation, substitute in the numbers, okay? Please do this, because if you make a mistake in your calculator, you can at least get this mark. If you haven't written this and you just get the wrong answer, you will have only got the 1 mark for the temperature change to the Kelvin. Okay, getting the value out, the volume in meters cubed or decimeters cubed, it'll give you 4 times 10 to the minus 5 meters cubed, but converting it into centimeters cubed, and giving it as a whole number, 40 centimetres cubed, that got you the 4th mark. But please do show your working for these PV equals nRT equations. Give a reason why the student repeated the experiment 3 times. I bet many of you would struggle to give an answer to this. You might be tempted to say, oh, fair test. But actually what it wants is to identify anomalies and discard them. To identify random errors and discard them. That's basically the idea there. Don't allow to improve the accuracy. Don't allow to make the results more precise, because it won't. You're recording it to the same precision every time. Allow to improve reliability or reproducibility. That was allowed in this case. Basically, the safest answer, I think, is to find and remove anomalies, okay? So if you can remember that, find and remove anomalies. That's probably the best answer to this. Give 3 reasons for the difference between your calculated value in A and the actual volumes of hydrogen gas obtained by the student. For each reason, identify a change to either the apparatus or the chemicals that could be made by the student to improve the result. So back on your CPAC, you were asked, what were the sources of error? Not mistakes, sources of error in this experiment. And we talked about things like you couldn't get the bung on immediately, so some gas would escape. We talked about the fact that your apparatus might be slightly leaky, your reagents might be impure. So in this case, not the hydrochloric acid, that's in excess, but the magnesium, which is your limiting reagent, might be impure, might have an oxide coating. The one thing you couldn't have in this case is that the hydrogen would dissolve in the water. I can't remember the exact details. Firstly, hydrogen doesn't dissolve in water. And secondly, I think you're collecting it in a gas syringe, although I haven't got the question in front of me right now. But be careful of that. So what did they want? They wanted hydrogen escapes from the apparatus. Use a sealed apparatus with a gas syringe. Okay. So you probably, this seems to imply that you were collecting over water. Can't quite see there. But using a gas syringe might prevent hydrogen escaping. Issue, magnesium ribbon covered with oxide. Yeah, that's the impure magnesium. So clean with the abrasive before you weigh it. Magnesium may be less than 0.04 grams. Yeah, basically huge source of error here. If you look at that, that is 1 in 8. So that's like over 10% error there just in the mass of magnesium, because we need to use, and this is right, a more precise balance or a larger mass of magnesium. We need to minimize the percentage error in weighing. Large measuring cylinder cannot measure volume accurately. Gradations are too far apart. Use a smaller measuring cylinder, burette, conical flask, bung with gas syringe. Okay. What have we got over here? Maximum of 3 marks for issues, maximum of 3 marks for improvement, which must be linked with associated issue or a near miss. Okay, so you can't get 6 marks if your 3 problems don't match up with your 3 improvements. Do not award impurities on magnesium. Okay, slightly harsh there. I would have thought that was okay. It wants you to specifically talk about the oxide coating. If more than 3 issues are given, maximum 4 marks if any incorrect chemistry is stated. So if your 4th one, unfortunately, gives something like not all the magnesium reacts, then you won't be able to get it. Ignore anything talking about the solubility of hydrogen, changes in temperature, changes in acid concentration, the air already in the apparatus, or measuring the length of the magnesium. They were not valid. Okay, so quite prescriptive there, but be aware the same thing's coming up again and again. And if you see lots of these exam questions, you will get the hang of it. This is a question here that I know a lot of students did struggle with. Aluminium reacting directly with chlorine to form a compound aluminium chloride containing only aluminium and chloride. Right, first thing to do here, guys, and the first 2 marks are from working out the empirical formula. So if we've got 0.101 grams of aluminium, that means that the amount of chlorine we must have in this is 0.399 grams. If we divide those by the relative formula masses, 27 and 35.5, we can see actually that there is a ratio of 1 to 3. So 0.101 divided by 27 is that. 0.399 divided by 35.5 is that. If you divide both of those by the smaller number, 0.37404, you get a 1 to 3 ratio, and it's a pretty good 1 to 3 ratio here. And you can therefore work out that the empirical formula is AlCl3. Now, it wasn't essential you did this. You could have got all 6 marks without getting these 2, but it was a safe way to get 2 marks if you then messed up on the second part of the question. So we now need to use PV equals nRT. We've got the temperature in Kelvin, that's fine. We've got the pressure in kilopascals, so we do need to convert that. So that is 100 kilopascals, so that is 100,000 pascals. We've got the pressure, we've got the volume, but we must put that in meters cubed, not decimeters cubed, meters cubed. So we need to divide that by 1,000,000, okay? And a really common mistake there, dividing it by 1,000,000. But then we've got the volume, so we can work out the number of moles because we're given R. And if we work out the number of moles there, we can proceed. Okay, so what have we done? Converts pressure into pascals, converts volume into meters cubed. That's your first mark. Rearrange PV equals nRT and finding the number of moles. Okay, so 1.8 times 10 to the minus 3 moles of this. We are told the mass that contributes to that number of moles. So just as we saw in my first video last week, if we've got MR is mass over moles, we know that we put in 0.5 grams of sample there. We know the number of moles of gas from there. So we can get that the relative formula mass is 267. Okay? Now, couple of things to state here. Firstly, if you had made a mistake and you forgot to divide your volume by 1,000,000 and you'd in fact divided that by 1,000 instead in decimeters cubed, that would be out by a factor of 1,000 and it should be obviously wrong at that point. So if you get a molecular mass that just looks ridiculous, just check your unit conversions. So if that's either 1,000 too big or 1,000 too small, in this case that number n would be 1,000 times too big, so your relative molecular mass would be 0.3ish. Okay, so it can't be, so you would know you'd made a mistake. Second thing, if you've already worked out AlCl3 is the relative formula mass, the empirical mass, it's quite easy to realise that if you divide that number by the mass of AlCl3, it gives you 2, so the formula must be Al2Cl6. However, there were people who managed to work out that that must be Al2Cl6, presumably using the valency of the fact that aluminium is in group 3, would form a 3+ ion, chloride would be 1-. Okay, so a bit of intelligence will go quite a long way here. And it does say, correct, if you get all these correct, and you get Al2Cl6 without the incorrect marking, you can get all 6 marks, even without the 2 points on the previous slide. Got another table here. The only difference here is we've got a 5 mark. You've seen these at GCSE. Calculate the average titer, use the concordant results, then do a titration, all in one. So 1 mark for getting the titers correct and recording them. Look at this, 24.00. Do be careful, it needs both those zeros to be correct. 1 mark for calculating the correct mean titer. 1 mark for calculating the number of moles of sodium carbonate in 100 centimeters cubed, and therefore dividing that by 10 to get the number of moles in 10 centimeters cubed. I bet a few of you forgot to divide by 10 there. Moles of hydrochloric acid, therefore just straightforward titration, remembering that the sodium carbonate reacts in a 2-to-1 ratio with hydrochloric acid. And finally, therefore, concentration of hydrochloric acid using concentration is moles over volume to give you 0.102 moles per decimeter cubed. Allow 0.1, provided working given, does give that answer. Correct final answer with an alternative route scores 3 marks. Allow transmission error on incorrect mean titer. So, you know, if you calculated the titers, you got the wrong mean because you used, I don't know, all of them, you could still get 4 out of 5 marks on this. Colour change at the end point when methyl orange is used as an indicator for this titration is right, C. Now, I do want to clarify something that I got wrong in my video. I talked about methyl orange going from yellow in alkali to red in acid, where it is orange in the middle. Okay, and I said, I think, you know, the correct colour change, make sure you go yellow to red or red to yellow. Orange is also acceptable. Actually, my mistake was they want the endpoint to be orange in this case. So the only correct answer is it goes yellow because it starts off alkaline and it ends up orange, which is at the neutral point. Yellow to red is not correct because this is going beyond the end point into an acidic solution. So do watch that. It's yellow to orange. They want you to talk about stopping at that neutral point rather than the other way round. Explain 3 actions a technician might take in the procedure just before the end point of the titration to ensure that the volume of acid added at the end point is accurate. So just before the end point of the titration, what might the technician do? Well, the obvious things you might think about are swirl it, add the solution drop-wise. So add drop by drop, you should have got that one. And it does say explain so that too much is not added. A second one you should have got is you should swirl it, shake it, or agitate it to ensure that the reaction is going well. Do not award to make the reading more precise or accurate. Do not award ensuring the burette is vertical, measuring to the bottom of the meniscus, because that's not at the just before the end point of the titration. Parallax errors. So all of this is kind of reading the burette, but that's not right before the end point of the titration. You could have all had use a white tile, use paper so you can clearly see the colour. You could have had compare the colour of the solution with previous titrations to check the colour is the same. It's not one I would have got, but it's allowed there. But the one that you might have got, and this is a sensible one, is rinse the end of the burette with distilled water into the conical flask to ensure that all the hydrochloric acid is in the conical flask. Okay, so something that we probably didn't do in the lab, but you can rinse the end of that jet into the conical flask. Make sure all the acid, all those drips on the end of the burette are actually in the conical flask. Write the equation for the reaction between calcium carbonate and hydrochloric acid, including state symbols. So calcium carbonate solid, 2 hydrochloric acid aqueous, not liquid here. The only time you'd use liquid is in the group 7. Calcium chloride, right, you do need to know that is of course a soluble salt. All halides are soluble with the exception of lead halides and silver halides, plus water, which is a liquid, and carbon dioxide, which is a gas. They did allow you to write the ionic equation. Calculate the molar mass of calcium carbonate. It's one that you possibly even know off the top of your head here. 100 grams per mole or 100.1 grams per mole. No problems with that, except answer with no working. Units were optional. Show that in each experiment the hydrochloric acid is in excess. Okay, you had to do a couple of things here which were fairly straightforward. The first thing was you had to show the maximum mass of calcium carbonate you used was 0.5 grams. So the maximum calcium carbonate is 0.5 grams divided by 100, which is 0.005 moles. You've also got to take into account the fact that it is a 2-to-1 ratio. That means you always need at least 0.01 moles of HCl. Okay, so you did have to take the ratio into account for full marks here. So let's have a look. Calculate the moles of calcium carbonate in 0.5 grams for 1 mark. You should have been able to do that, no problems whatsoever. But then for the second mark, you had to show the number of moles of hydrochloric acid in 20 centimeters cubed and show it is in excess with appreciation of the 2-to-1 ratio in the equation. And a lot of people didn't do that. The other thing that a load of people did in this question when they were given it was they just wrote down a load of maths. And I would have got things like 0.005 is greater than 0.04. Sorry, is less than 0.04. That really isn't sufficient. You need to explain what these numbers mean, okay? So just be careful there. Plot a graph of volume of carbon dioxide produced against mass of calcium carbonate on the grid. Include a line of best fit. State how your graph supports the idea that the volume of gas produced depends directly on the mass of calcium carbonate added. So, plotting the graph, include a line of best fit, 2 marks there. How does it support the idea that the volume of gas produced depends directly on the mass of calcium carbonate added? Right. We need, therefore, to show it is directly proportional. This bit, proportional, is a straight line, but directly proportional means that 0 on one will give you 0 on the other, and therefore it must go through the origin. So there we go, points plotted accurately and axes labelled for 1 mark. Plotted points must cover more than half the graph paper. I draw your attention to that. Reasonably straight line of best fit, which may extend to the origin, 1 mark. Acceptable answer here, straight line through the origin, therefore volume directly proportional to mass. Allow a positive correlation. I would be wary of saying that. Because they want you to show it depends directly. So they really do want you to say it's gone through the origin. Calculate the volume under these conditions of 1 mole of carbon dioxide gas from these data. Give your answer in decimeters cubed to 2 significant figures. Some people really struggled here, but look, we know 0.5 grams of calcium carbonate, in other words 0.005 moles, gives a volume of 100 and what are these fours? Something like 115 centimeters cubed. So we know that that number of moles of calcium carbonate, which from the equation back here, calcium carbonate to carbon dioxide is a 1-to-1 ratio. So we know that 0.05 moles is not just of calcium carbonate, but is of carbon dioxide. And we are just asked for the molar volume. So if 0.005 moles gives 115 centimeters cubed, then 1 mole gives us how many? Well, we times that by 200, we times that by 200, and we get 2,300 centimeters cubed, which is 23,000, which is 23 decimeters cubed. It asks for it to 2 significant figures, don't forget that. So there you go. They work from the gradient, but data can be used from any experimental number, e.g. using experiment 5. Moles of calcium carbonate, 0.005. The volume that produces 115 gives you 23 decimeters cubed. Give a reason why the student added a small pinch of calcium carbonate to the acid before starting the reaction. Lots of you, first time round, really didn't get this right. Small pinch of calcium carbonate is there just to saturate the liquid, because we're generating carbon dioxide, and otherwise the initial amount of carbon dioxide that's going to be produced in this experiment will dissolve in the water and will collect less gas than intended. So to saturate the solution with CO2, to stop any CO2 formed from dissolving. That's the answer there. I hope this was useful. I hope that these questions reminded you of the level of detail you need to do, and that actually after seeing this you found fairly confident. There's another video that will be coming out next to this one, which goes through the multiple choice questions. We've been specifically told not to set you any homework over Easter, so I won't do that. But you will see me in about 2 weeks' time, and we'll start going through topic 8, Hess cycles. Hope you are well until then.